Welcome to Bell Labs. AT&T maintains a network control center in Bedminster, New Jersey. The control center staff work from a wallboard, a display that shows what's happening in the network. Inspired by this, Bell Labs statisticians have been searching for ways to analyze large amounts of data and to display it in ways that humans can quickly understand. In this video, we will learn about seenet, a computer program that displays network measurements obtained from the AT&T network. We will also have a look at CI-seenet, a packet switch data network in the Midwest, and FTS-2000, a network that combines voice and data for the federal government.
Our motivation for inventing seenet was a very practical problem of trying to understand the mass of data available to us from the AT&T switched network, about 1.5 megabytes of numbers every 5 minutes.
A network is a set of nodes connected by links. In the AT&T long-distance network, the nodes located around the country are digital computers that switch calls, and the links that connect those switches are the long-distance fiber optic cables.
This display concentrates on the links that join the network nodes and shows the links as colored lines on top of a map. Each line connects a source node with a destination. 4 colors encode the number of calls: blue for the smaller counts, then green, yellow, and red for the largest counts.
This graph shows that people make most of their calls in the morning and afternoon, and that the call volume falls off at noon.
These rectangles show the daily calling pattern for each node. The nodes are represented by rectangles, sized by the number of calls processed in each time period. People are waking up on the East Coast. Now the West is waking up and the East goes to lunch. Calls are building in the afternoon and then decreasing in the evening.
Because seenet is designed to help the network managers, our link display closely resembles the maps on the wallboard.
This is the way the wallboard looked at 10 o'clock the night of the California earthquake. The network managers applied controls to limit calls into the Bay Area to make sure calls could get out.
The lines on the map show the calls that couldn't get through. When you try to show this much information on a map, it's hard to draw any conclusions. There are too many lines. seenet allows us to get rid of the least important lines, those representing the smaller number of blocked calls. It's now clear that the biggest problems are situated on the West Coast.
To see the middle of the country, we can shorten the coast-to-coast lines. Now we can see all of the nodes, and we can tell the directionality of the blocking. Since all the lines are pointing east-west, we can see that the north-south calls are not being blocked.
Because of the earthquake, we know that calls to and from California are going to be blocked. Suppose we eliminate all the lines associated with California. Then, as we deactivate them, the nodes turn into cyan-colored diamonds. There are no lines left on the display, meaning that blocking hasn't spread beyond California.
Because important information can be hidden in any single view, seenet allows us to look at several displays at one time. This display shows overall network blocking at 7:50 p.m. on the day of the earthquake. And the other display shows blocking everywhere but California. As new data comes in at 7:55, we see a minor problem in Wichita. And at 8 o'clock, the increased number of lines shows that the problem has gotten worse. We know it's a relatively minor problem because the lines are blue. There are 4 blocked calls from Wichita to St. Louis and 2 from St. Louis to Wichita. We would have missed this problem if we had been watching only this display.
It was important to see how traffic flow changed in response to the protective strategies we used to deal with the earthquake emergency.
We can help the network managers visualize these traffic flow changes over time. Red and orange means things are getting worse. Gray, about the same. And green, better.
The goal of our ongoing research has always been to do a better job of displaying data. Our node display can show how data packets go through the CI-seenet regional network that connects universities in the Midwest.
In another experiment, we have incorporated sound with the visual display. It causes a click with every new set of data. We expect the picture to change with every click, but instead it changes every 3 clicks. Without sound, we wouldn't have detected this subtle feature. Although we originally conceived of seenet as a system for visualizing the AT&T long-distance network, we designed it from the start to be applied to a wide range of situations.
AT&T was building the FTS 2000 network to carry voice and data for the federal government. I used S, a powerful programming language, to provide the building blocks, and seenet to display the data. A system for servicing and engineering the network was up and running in a few months.
seenet, a valuable tool for understanding data. Its flexibility, interactive operations, and adaptability to different networks, CI-seenet, FTS 2000, and AT&T.